we're back on section 4.3, and there are a few theorems that are consequences of the mean value theorem. Theorem 1, f prime of x equal to 0 for if f prime of x is equal to 0 for all x in a and b open in interval, then f is constant on a and b. Theorem 2, if f prime is bigger than 0 for all x in a and b, then f is increasing on a and b. Theorem 3, if f prime of x is equal to g prime of x for all x in a and b, then f of x is equal to g of x plus c, where c is some constant. So now let's try to prove these using the mean value theorem. These proofs come in handy when you're in higher level mathematics. They come in handy a lot when you're taking numerical methods and in analysis, mathematical analysis, and some of the courses have similar proofs that even in linear algebra and diffie sometimes similar proofs, not quite like this, are you see, but in numerical methods and mathematical analysis, you see more proofs that are a lot more similar to these proofs. So let's prove part 1. Suppose that a and b are arbitrary numbers, and a and b are between capital A and B are between lowercase a and b is bigger than a. Now let's write down, because all the conditions for mean value theorem is true, let's write down the mean value theorem for the capital A and B. If we write the mean value theorem for capital A and B, we get that there is a point C between the capital A and B, such that f prime of C is equal to the average rate of change between A and B. But then f prime of C is going to be 0. We know that f prime of C is the hypothesis, and therefore, if I multiply both sides of the equation by b minus a, I will get that f of b minus f of a is going to be 0. That is, f of a is going to be equal to f of b. So that proves the first theorem, because it says for any 2 points between the a and b, and we can pick between the lowercase a and b, we can pick, we can find that the 2 points give you the same output. Now let's do part 2 of the theorem. And this time it's asking if f prime of x is bigger than 0 for all values in a and b, then f is increasing on a and b. In this case, let's again choose a and b between capital A and B, between a and b, and this time assume b is bigger than a. And then again, writing the mean value theorem, because it works, we end up with f of b minus f of a over b minus a. Again, multiply both sides by b minus a, and then you get f of b minus f of a, and let's remember we chose b minus a to be bigger than 0. So this time f of b minus f of a is going to be b minus a times f prime of c. F prime of c is bigger than 0, b minus a is bigger than 0, so f of b minus f of a is bigger than 0, which means that f of b is bigger than f of a. So this is something that we've been using so far a lot, and most of these we've been using a lot, part A and part B, but we didn't know that they were a consequence of mean value theorem. And so part B of the theorem basically says if f prime is bigger than 0, then f prime is increasing on a and b. Now let's do the last part of this. And so let's say if f prime of x is equal to g prime of x, and then we want to prove that f prime is equal to g prime plus a constant. So form the difference function. See, the other two only were involved in with one function, and we're experienced from intermediate value theorem. When we see two functions, we take the difference, and we did this for mean value theorem a few times too. Now take the difference function, and then the difference function, and since f prime and g prime are equal to each other, the derivative of difference function is going to be 0 and for all values between a and b. And so when the derivative of the difference function is 0, by part 1 of the theorem, that difference function has to be a constant function. And so now write down difference function as f of x minus g of x equal to c, and then add g of x to the other side, and you get f of x plus g of x. F of x is equal to g of x plus c. And that proves the theorem.